Let's continue from example 13. 2-point charges, a 4e and a plus 4e and a plus e are fixed at a distance a apart. A third charge q has to be placed in the line joining the two charges so that it may be in equilibrium. Just the system need not be in equilibrium. The previous sum that we were discussing was about the system being in equilibrium. But here only the central charge that you're inserting has to be in equilibrium. Supposing you're placing a charge q. Supposing you're placing it at a distance of x, and this will be a minus x in this sum, okay, because a is the distance. And you know, if it's positive charge, this 4e is going to be, the 4e is going to be repelling it towards the right. This is force due to 4e, or let's call it as F1. And the small e is going to be repelling it on the left side, and this is going to be F2. And the net force has to cancel out each other and become equal so that the net force on charge q will be 0 and it will be in equilibrium. So let's do what is F1. F1 is 1 by 4 pi epsilon naught into 4e into q by x square. Should be equal to 1 by 4 pi epsilon naught, or you can even put k, small q into small e by a minus x the whole square. So 1 by 4 pi epsilon naught get cancelled, e get cancelled, q get cancelled. So you get 4 into a minus x the whole square is equal to x square. On taking a square root, you get 2 into a minus x is equal to x. So 2a minus 2x is equal to x. 2a is equal to 3x and a is equal to 3x by 2. See, actually speaking, when you take a square root, you will get a plus or minus. You can also get 2a minus x is equal to minus x. 2a minus 2x is equal to minus x, and 2a will be equal to x, and a is equal to x is equal to 2a and x is equal to 3, but we are placing it between. It cannot be 2a, it cannot exceed this, because if I'm going to place a charge q, it will get repelled by the small e, it will get repelled by the 4e, it's not cancelling out, so it doesn't make sense to write like this. So otherwise mathematically it's correct, but in physics it's not right. So a is equal to 3x by 2. So x is so x is equal to 2a by 3. So thus you understand that you're placing it at a distance of 2a by 3 from 4e. So now that you've understood that, so then that particle will be in equilibrium. Okay, let's study more. Okay, now the force exerted by 4e is F1. The force exerted by E is F2. Supposing I'm going to move this charge slightly towards the right, this distance increases in that case, right? So there, because of which F1 decreases, F2 increases, and F2 minus F1 will be the net force which will act on it, and F2 is greater, so the net force will also be along the direction of F2. Therefore, even if it displays towards the right, since F2 minus F1 will act towards the left, it will get displaced and come back to its equilibrium position. So that is why it's called stable equilibrium position. This is why it's called, this equilibrium is called stable equilibrium. When you insert a positive charge, what happens when you insert a negative charge? Let's see. So the same sum, 4e and a e. I'm going to insert a negative charge, and you know that this 4e is going to be attracting it. It's just F1. That small e is going to be attracting this, which is F2. Even then the forces will get cancelled. The same location, x is equal to 2a by 3, is when they'll cancel out. There's no difference in that. But let's now study whether what happens when it displays this minus q to the right. When displays the minus q charge particle towards the right, that's towards E, you know, this R increases, and because of which F1 decreases and F2 increases as usual. There is a net force F2 minus F1. But you know, F2 is acting towards the right. So when it displaces towards the right, it's further getting moved only towards the right and is not coming back to its original equilibrium position. So this is not stable. This is an unstable equilibrium. If I move it, then the equilibrium is getting disturbed. So when I insert a minus q, it is becoming unstable equilibrium. I hope you understood. This is a very beautiful sum. So let's go to example 14. Should I do example 14? No, I'm not going to do similar sums, so just leave it like that. You understood? The previous sum that I did was the system has to be in equilibrium. This sum that I did is a charge particle alone, the central charge particle alone can be in equilibrium. So that's about it. Okay, so next is example 15 I'll do. 2-point charges of value capital Q and small q are placed at a distance x and x by 2 from a third charge 4q. Oh, there's a third charge 4q from which at a distance of x by 2 and at a distance of x. I am placing q at a distance of x and small q at a distance of x by 2. Read the question properly. 2-point charges of charge capital Q and small q are placed at a distance of x and x by 2 from a third charge 4q, all the three being in the same straight line. Calculate the magnitude and the nature of the charge q such that the net force experienced by the charge q is 0. So the net force experienced by the charge q has to be 0. They are all going to be lying on the same straight line. Okay, so then let me mark this q here, capital Q here, and the total distance is x. This is x by 2, obviously this will also be x by 2. The net force experienced on this has to be 0. You know 4q and q is going to be repelling. It's going to be pushing away the q. The capital Q is also positive charge, so it's also going to be repelling. Calculate the magnitude and nature of the, the question is about this q. So I don't know, but if this has got to be in equilibrium, if I know 4q is positive and q is also positive, it's going to be repelling like this. This has got to repel if this has got to repel, and therefore q has got to be positive. Very, very simple. That's when it will cancel out, correct? So we know that capital Q has got to be positive. But let's look at what should be the magnitude of it. You know, this force will be F is equal to K into Q1 Q2, which is 4Q into Q by x by 2 the whole square, which should be cancelling out with the force with this, which is K into Q into capital Q by x by 2 the whole square. Only if this happens can the two forces get cancelled out, and this can be in equilibrium, because the question says that all the three charges being in straight line, calculate the magnitude and nature of the charge Q so that the net force experienced by Q, not the entire system, just the Q has to be in equilibrium. So Q and Q will get cancelled, K and K get cancelled, x square and x square get cancelled, x square by 2, everything is getting cancelled. So you get 4Q is equal to capital Q. So then the capital Q has to be 4 times the small q. That should be the magnitude, and it's got to be positively charged so that the small q can be in equilibrium. That completes this question. Let's go to 16th, example 16. Example 16, a charge q is to be divided into two objects, which means one is a charge q is divided into two objects. If one is q, the other is q minus q, x and q minus x, whatever. You can consider this as like this and this, it's your wish. So I'm dividing as q and q minus q, capital Q minus small q. Charge q is to be divided into two objects. What should be the values of the charge on the two objects? The force between the objects can be maximum. Oh, this is force has got to be maximum. You can't do it at this stage. I don't know. You know differentiation, right? But you don't know maximum minimum. When the differentiated value is equal to 0, then it pertains to maximum or minimum value. Okay, so then you know, when will the force between them be maximum? F is equal to K into Q into capital Q minus small q by the distance is r square. And if you know what is the variable here is small q. You will not understand this sum initially, but later as you do mathematics and then when you do physics, you will understand the small q is a variable, capital Q is a given constant. So then you can differentiate this as per the variable dq, small q, where k is a constant, r square is a constant, this and this are u and v, differentiated as u and v, q into capital Q minus, okay, capital Q is a constant. When you differentiate this, it will get minus 1. Capital Q minus 1, when you differentiate, Q will become 0, minus Q will become minus 1, plus capital Q minus Q into differentiation of Q will be 1. So then this has to be equal to 0 in order to be forced to be maximum. Differentiated value has to be 0. So Q should be minus Q, this should be equal to this. is equal to Q. Therefore, you should divide it equally so that the force can be maximum. That's when we get the maximum force. This is an entrance exam portion. Children who are struggling need not learn this sum. Only others should learn this. So let's go to next question. Next question, I want to do only the 18th question after this. 18th question after this. Two small spheres, each having a mass m and a charge q coulomb, are suspended from a point by insulating threads, each 1 meter long. 1 meter or L meter, I don't know. I think it's L meter long, but negligible mass. If theta is the angle each thread makes with a vertical. Okay, so then let's do small bobs are suspended. This is bob A and this is bob B. The angle that the thread makes with a vertical is given as theta. If this is theta, this will also be theta. And it's suspended by a thread. A thread will always have a tension. You all know that. There will be an mg which is acting downward, and two small spheres having charge q, which is this also q, this also q. Like charges will repel, the force of repulsion will be in this direction. So can you see that mg is acting downward, a force of repulsion in this direction, resultant between them will be in this direction. This is the resultant of these two, mg and f. Corresponding angle, if this is theta, this has got to be theta. Yes. And the question says you have to prove that q square is equal to 4 mg L square sin square theta tan theta 4 pi epsilon naught. Some proof like this is what you need to prove. All that you can write is, can you see this is a resultant? This is the resultant, and I would do this sum differently. I would not do it like how Aurora has done. I would mark this vector, and can you see corresponding angle tan theta? I'll write tan theta from here. You construct this into vector. From here you write what is tan theta. Is opposite by adjacent, which is opposite is f. Because if this is f, this has got to be f. Correct? And adjacent is mg. Tan theta is f by mg. And tan theta is equal to f. F itself is 1 by 4 pi epsilon naught. I don't write k because the question proof has got 4 pi epsilon naught. Into q1, q2, which is q square. By the separation between them, here comes a separation question. What do you know about the separation? We don't know the separation. But you know this is theta. And this is L, length L. Suspended length L. Therefore, you can do from this triangle, you can write what is sin theta. Sin theta is equal to this opposite side, just a part of it, x by L. So, x is equal to L sin theta. Therefore, the total separation will be 2L sin theta. So then you can write q square by r square, which is 2L sin theta the whole square, by mg, by mg. So then from this you have to write what is an expression for q square. Just cross multiply everything, you directly will get this answer. It's very simple. I'm not doing Aurora's way. My way is very simple. I hope you learn my way, okay? So that's all, guys. With one topic is over. The next thing that I'm going to teach you is about superposition of forces. Superposition principle, vector form, Coulomb's law in vector form. So those are the things which I am going to take next. Okay. So coming back to Coulomb's law in vector form. So you have x-axis and a y-axis. You have a charge q1. You have a charge q2, which is at a position vector r1 and r2 are the position vectors from the origin. This x-axis and this y-axis. You know that the two charges may be like charge or unlike charge. It will exert force on each other. Q1 will exert a force on Q2, which will be called F21. Its affected party is 2, so F21. Okay, and the Q1 is going to exert a force on Q2, which will be F21. And the distance, the position vector, this is r1 vector, it's in this direction. This is r2 vector, which goes from in this direction, you know, this is the direction. And this is the direction in which you're measuring is r12. The position vector, the distance between 1 and 2 is r12. That's how we write. Some teachers do write it as r21, but I write it as r12. And I want to write F21, which is a vector in vector form, which is 1 by 4 pi epsilon naught into Q1 Q2 by R12 the whole square, R12 vector the whole square. And from this is a triangle law. Can you see, if a triangle law, this is in same direction, this is same direction, this is same direction, this is an opposite direction, and therefore you know R1 plus R12 is equal to R2. Same direction is equal to, sum of the same direction is equal to opposite direction vector. Therefore R12 is equal to R2 vector minus R1 vector. So this is the conclusion. So you can also write this as F21 as 1 by 4 pi epsilon naught into Q1 Q2 by R2 vector minus R1 vector the whole square. But thing is, when you square a vector, it will become a scalar. Therefore, you have to write R12 cap. Just to represent, continue to represent it as a vector, you have to write R12 cap on the side. R12 cap, okay. So that's about F21 vector. Okay, so now or you can also multiply and divide by, in other words, it's 1 by 4 pi epsilon naught into Q1 Q2 by R2 vector minus R1 vector the whole cube into R2 vector minus R1 vector. Multiplying and dividing by the, then you don't have to write the cap because it will still remain to be a vector. You can write like this. So this is what it is. So supposing you have the same Q1 and same Q2 here, and Q2 is going to exert a force on Q1, it will be F12, and its position vector will be R21 vector. Okay, and this is R1 vector and this is R2 vector, and as usual you can write F12 to be 1 by 4 pi epsilon naught into Q1 Q2 by R21 vector the whole square into R21 cap, or 1 by 4 pi epsilon naught into Q1 Q2 by R1 vector, R21 is R1 vector by triangle law, R1 vector minus R2 vector the whole square into R21 cap. Different ways of writing, by multiplying and dividing by R1 vector minus R2 vector the whole cube into R1 vector minus R2 vector. You can multiply and divide, thus you get this. Okay, so these are all this is the way we represent Coulomb's law in vector form. Coulomb's law in vector form, but it's never been asked anyway. Okay, then next is superposition of vectors, superposition of forces. Supposing there are many particles, a number of particles, not just two. You have a particle which is Q1, Q2, Q3, Qn, and so on, many particles, Q1, Q dot dot dot, okay, Qn. Each one will exert a force on each other. So let's look at the first one. On the first particle, that Q2 will exert a force on one, Q3 will exert a force on one, a Qn will exert a force on Qn. Let's keep Qn differently, like this. Qn is going to exert a force on n. So there are many forces, which is this is a force F on 1 due to 2. This is a force F on 1 due to 3. This is a force F on 1 due to n. Like that, the second particle can also undergo force. Okay, let's come to this force. The force on 1 due to 2, due to 3, due to 4, there will be many forces. The F1 vector, the net total force on the first vector is F1 2 plus F1 3 plus F1 4 plus dot 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 F1 n. That's a force on the first charge. So let's look at the second particle then. Okay, so second particle is like similar diagram again. You have a Q1, you have a Q2, you have a Q3 and a Qn. Second particle, there's a force like this due to F21, second particle due to the first particle. Force on the second particle due to the third particle. Force on the second particle due to nth particle. So the force on the second particle will be F2 due to 1, F2 due to 3, F2 due to 4, F2 due to nth. Like that it goes on, correct? So then therefore the total force F, which is the force exerted on all particles, which is what to say, the principle of superposition states that when a number of charges are interacting, when a number of charges are interacting, the total force on a given charge is the vector sum of the forces exerted on it due to all other charges. Okay, so that's the definition. When a number of charges are interacting with each other, the total force on one charge will be the vector sum of all the forces will be the vector sum of all forces due to other charges on this charge. I hope you understood. So that's so then what this is known as principle of superposition. So we can write a general formula. The net force in the entire system, therefore F net on the entire system will be always between two charges, 1, 2, 2, 3, like that, be two charges where we can call one as A, another as B, and A is never equal to B because one will not exert a force on one itself. Yeah. So then therefore the general formula is 1 by 4 pi epsilon naught will be common for everything. The Q1, Q2 will be QA and QB, where A is never equal to B, correct? By R square, 1 by 4 pi epsilon to Q1, Q2 by R square, which will be RA minus RB, say RA minus RB the whole cube, the vector the whole cube, into RA vector minus RB vector, and a summation here where A is not equal to B. A is 1, B can be 2, A is 1, B can be 3, and so on, where A and B can range from 1 to n. A and B together can range from 1 to n. And this is the formula, a general formula for superposition of charges, where all the particles will exert force on one another, and there will be net force, and this is the total force on the system. Okay, so that's about it, and let's do some numericals in this. Let's do example 19. Example 19, an infinite number of charge, each equal to 4 microcoulomb, are placed along x-axis. At x is equal to 1, then x is equal to 2, x is equal to 4, x is equal to 8, and so on. An infinite number of charges, each of 4 microcoulomb, is placed everywhere like this along x-axis. Okay, find the total force on the charge of 1 coulomb placed at the origin. So you're placing a 1 coulomb of 1 coulomb. There's a microcoulomb. This is just 1 coulomb. Okay, a 1 coulomb of charge is placed at the origin. The force exerted by this due to this will exert a force on this will exert a force on this will exert a force on this. It's a force exerted only on 1 coulomb, not among each other, you know. It's not a force between every charge. It's a force that is exerted on 1 coulomb. Let's, due to the position 1 will be 1 by 4 pi epsilon naught into 1 coulomb into 4 microcoulomb, 1 coulomb into 4 microcoulomb. So it's Q1, Q2 by the distance will be R1 square, okay, R2 square, and so on. So let's write the charges itself. It's 1 into 4, 4 into 10 to the power minus 6, 1 coulomb by the distance, which is 1 square. If you consider it as in meters, yeah, it's in meters, so it's 1 square plus this one, second one, 1 by 4 pi epsilon naught into same 1 into 4 into 10 to the power minus 6 by distance will become 2 square plus 1 by 4 pi epsilon into third charge. That distance will be 1 by 4 pi epsilon into other 1 into 4 into 10 to the power minus 6 by 4 square, and so on. Okay, so and it goes on like that, And so what is common is 1 by 4 pi epsilon naught is common. 1 into 10, 1 into 4 into 10 to the power minus 6, we can ignore the 1 because it's anyway 4 into 10 to the power minus 6 can be taken out common. You get 1 by 1 square plus 1 by 2 square plus 1 by 4 square plus dot, it goes on like that. And this is like 1 by 4 square. Can you see that this itself forms a GP? This itself forms a GP, and you know that infinite series, as sum of infinite series of GP is A by 1 minus R. A by 1 minus R. So 4 into 10 to the power minus 6, 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into A is just 1 by 1 minus R. What is R? Second term by first term. Second term by first term. First term is just 1 by 2 is R. Second term by first term. Let's see, 1 by 16 by 1 by 4. Oh no, 1 by 4 by 1 by 1. So it's 1 by 4. I'm sorry. R is second term by first term is 1 by 4. 1 by 4 by 1 is 1 by 4. So then therefore we'll take LCM. This will become 3 by 4. So it will become 4 by 3. 4 into 10 to the power minus 6 into 9 into 10 to the power 9 into 4 by 3. And whatever this answer is, 4.8 into 10 to the power 4 newtons. This was an IIT question. I'm done at example 20. Consider 3 charges Q1, Q2, Q3. Each of charge Q, all of them of equal charge. So then they're placed on the vertices of an equilateral triangle. So you place this, and it's just 1 meter of side L. No, it's not 1, it's side L. What is the force on a charge Q placed at the centroid? Capital Q is placed. What is the force on it? Okay, so you know that there will be a force exerted like this due to this charge, repulsive. There's a force exerted by this due to repulsive. This is also going to repel it. And you know, by Lami's theorem, the net force will be 0 because they're all, this is 120 degree. And the resultant upward will be at exactly above, and this is going to pull it down. And so then I can say the net force is equal to 0 as soon as I see this. As soon as I see this, I can say that. Otherwise, what you have to do is you should write that this angle is 120. And therefore the resultant here will be like this upward. And therefore this will be downward, and the resultant, this is F1, so let's call it as F1, and this is also F1 because this is also F1. All of them, or we can even call it as F. Can you see, all of them are equal charges, and because K into Q into capital Q by this distance, whatever that distance is, yeah, everywhere. So you can say all of them are same force, and you have this 120 degree here. So by using parallelogram law, you know that this is F and this is F, and angle between them is 120. The resultant F upward is equal to root of F square plus F square. Parallelogram law will have plus 2F square cos 120. Cos 120 is minus 1 by 2. So when you substitute minus 1 by 2 in the place of cos 120, 2 and 2 get cancelled. It will become minus F square. So you'll get an F. You will just F of downward F is also F only, na? So they both will just get cancelled. Upward is F and the downward is also F, and so they both will get cancelled, and so the net force acting on it is 0. This is the way I would do the sum. It's very simple. I wouldn't even write 1 by 4 pi epsilon naught. All that is not necessary. You know it's K into capital Q into small q by the distance, whatever this distances are. You know, let's consider this distance as x in that case, and it's x square, and they are all equal, and so we can call it as F, F and F, and this is the way I would do the sum. So the net force acting at the center is 0. So let's go to example 21. 3 point charges plus Q, each are kept at vertices of an equilateral triangle of side L. Plus Q. All of them are positive. Determine the magnitude and the sign of the charge to be kept at the centroid, so the charges, the vertices will remain in equilibrium. What should be the charge I must place at the centroid so that the charges at the vertices can be in equilibrium? See, supposing I'm assuming it as a positive charge, say. Okay, this is going to be repelling it. This is going to be repelling it. This is going to be repelling it. Where is the question of the charges would remain in equilibrium? So it cannot be plus q. It's got to be negative q. It's got to be a negative q, so that this charge will get attracted like this. This charge will get attracted like this, and this charge will also get attracted like this. While this charge is going to be repelling it. The small q and small q is going to be repelling it. This small q and small q is going to be repelling it. And the resultant will be upward, and that will be countered by this downward arrow that I have put here. If it's attractive, when these two charges repulse it, the repulsive upward force, resultant upward force, the angle between them will be, this is 60 degree. In that case, the resultant, which is in the upward direction, this will be F is equal to root of, again I'm going to call it as F only. Each force is F because it's Q square by R square. So these forces I can call it as F and F because it's between small q and small q. This is also small q, small q, small q, small q. So I can call it as F. And so then the resultant will be root of F square plus 2f square cos 60. Cos 60 is 1 by 2. So 2 and 2 get cancelled, become root 3 f square, which is root 3 f. So if you can remember, in 120 degree the resultant will become f. But in 60 degree the resultant will become root 3 f. This is the moral of the story. If you can remember it, very good. So the resultant is root 3 f. And the same root 3f should be the downward red color force that it should experience, root 3f. It should be the force that it should experience for the system to be, for the charge particle q to be in equilibrium, small q to be in equilibrium. So then therefore, I want to find what should be capital Q, right? The question is to find what should be capital Q. So let's find this red color's force, which is an attractive force, which will be K into capital Q into small q by that distance, which is just x square. Yeah, that's the distance, x square. We'll figure out what is that distance next. Okay, K into capital Q into small q by that distance should be equal to root 3f. So with this you can find what should be q, but we should know what is x. We randomly assumed as x in the previous sum because I didn't need it, but here I need it. I need to write what is x. So let's come here, let's learn this. You have an equilateral triangle and this is a centroid, okay? This is a centroid and you want to find this distance. You know, this will be 30 degree. Just construct like this, okay? And you know, if this is L, the whole length is L, this will be L by 2. And take this right triangle. And if you want to find this side, which is the hypotenuse, you can write sine 30. No, you have to write cos 30. The cos 30, which is equal to adjacent, which is L by 2 by hypotenuse. Thus the hypotenuse will be L by 2 into cos 30. And a cos 30 in itself is root 3 by 2. So L by 2 into root 3 by 2. So it's root 3 L by 4. So that distance itself is root 3 L by 4. Am I doing it correctly? Let me check, verify that once again. Cos 30 is equal to L by 2 by hypotenuse. So cos 30 itself is root 3 by 2. So root 3 L by 4. One second, hold on. I made a small mistake here. So then cos 30 is equal to L by 2 by hypotenuse. So hypotenuse is equal to L by 2 by cos 30. And a cos 30's value is root 3 by 2. So substitute root 3 by 2, 2 and 2 get cancelled, L by root 3, so mug it up. This distance from the centroid will be L by root 3. So substitute that here, it's K into capital Q into small q by L by root 3 the whole square is equal to root 3f, from which you can find what should be the value of q. Because f itself, what is f? F itself is k into, what is it? K into small q into small q square by L square, F, I told you this F will be between small q and small q. So substitute so that you can cancel the k and k. You can cancel the small q. You can cancel the L square and L square. This will become 3, of course. And the root 3 and 3 will get cancelled. So you get a root 3 q is equal to small q. And it has got to be negative charge. The capital Q has to be minus q by root 3. It's a very, very important sum, such a beautiful sum, where you should remember that this part centroid, this distance is L by root 3, then you're sorted. You can do the sum very fast. The moral of the story is whenever there's the angle between the two vectors is 120, you get the resultant force as F only when you substitute parallelogram law. When angle between them is 60 degree, you get the resultant as root 3F. Then in a centroid, from the vertex to the centroid, the length is, if the length of the equilateral triangle is L, then is L by root 3, and this help you to solve the sums faster. So let's do example 22. Example 22, consider charge Q, Q and minus Q placed at the vertices of an equilateral triangle. So there is a charge which is minus Q, there is a plus Q and a plus Q placed at the vertices of an equilateral triangle. What is the force on each charge? This plus Q is going to be attracting the minus Q in this direction. This plus Q is going to be attracting the minus Q in this direction. Okay. Does it say anything about the equilibrium? Consider charges, vertices on an equilateral triangle. What is the force on each charge? That's all. The force on each charge. No charge is in equilibrium. You just don't have to worry. So the force on this charge, the angle between them is 60. So you just have to find the resultant, which will be downward. And I told you 60 means root 3F. Correct? It's root 3F. If one charge, this force is F and this force is F. We can call it as F because it's Q and minus Q, and this is also between Q and minus Q. The resultant is root 3F. That's the resultant force which is acting downward on the minus Q charge. Let's look at this lift charge. This is going to be attracted by minus Q and it's going to be repelled by the plus Q. So the resultant will be in this direction, and the angle between them is 120 degree. So the resultant will be just F. If this is F and this is F, the resultant has got to be F, that. And similarly, this will also get attracted, get repelled, and the resultant will be F. And therefore, this is F, this is F, and a downward is root 3F. And these are the individual forces. What is the force on each charge is what they're asking. So that's about it. Okay, so that's about it. These are the directions and you can specify it. What is the force on each charge? Okay. Because they haven't really given what are the charges Q1, Q2 and all, just leave it like that. Okay, so let's go to next sum. Is the example 23rd. Plus 5 microcoulomb, 10 microcoulomb and minus 10 microcoulomb are placed in air in the corners of an equilateral triangle. Determine the resultant force on charge A. So it's the same, supposing there's a charge A, B, C like this. Resultant force only on A. It's if this is positive and this is negative, that the A will get pulled like this and it will get repelled like this and the resultant will be in this direction. And their magnitudes are, this is 10 and this is plus 10 microcoulomb, minus 10 microcoulomb, and this is plus 5 microcoulomb. And therefore you can call this also as F and this also as F, no harm, because it's between 10 and 15, 10 and 5 and minus 10 and 5. So the directions have been taken into account, so therefore you don't have to take the negative charge into account. The resultant will be, this is 120 and therefore 120 means the resultant will be just F. The resultant will just be F. And what is F is 1 by 4 pi, either of the charges, it's 1 by 4 pi epsilon naught into 10 into 5 microcoulomb. So 10 into 10 to the power minus 6 into 5 into 10 to the power minus 6 by the distance, whichever the length has been given as 5 centimeter, 5 into 10 to the power minus 2 the whole square. Thus you can calculate. I'm not doing this sum, it's similar to that, so I'm not doing it. Let's go to next sum. It's again on the vertices of a square. And the similar sum again I'm not doing, I'm just doing a rough recap. On the vertices of the square you have the charge Q1, you have a charge Q1, Q2, Q3 and a Q4. The question is about how is the Q4 getting affected, and they've given that the point charges 16 microcoulomb are placed everywhere. So then it's going to be repulsive. This is going to be repelling it. This is going to be repelling it. This is also going to be repelling it. Already you have you already have an F1, an F2 and an F3. F3 and an F2, sorry, F3 and an F2. You already have 3 forces and you have to find the resultant of all this. If you take F1 and F3 alone, the resultant of it will be root of F1 square plus F3 square. Now that has to be added with F plus F2 so that you get the net force. I hope you understood. So then what is F1 will be between Q1, Q4 by this distance. This distance is straightforward. In a square, side of a square has been given. It's given to be 0.2 meters. So then you know this is also 0.2. F1 and F3, the charges are same, the distance is same. So they are just going to be F, you can call it as F1 and F1 only. You don't have to call it as F1 and F3, or you can call it as F and F. And the resultant between them will be root of F square plus F square because it's a right angle triangle. Can you see what to say? The resultant, the angle between them is 90. If you do parallelogram law, is root of F square plus 2F square cos 90. Cos 90 is 0. So F square plus F square is root of 2F square minus, root of 2F square, which is root 2F. Oh, here it's root 2F, yeah. It's root 2F. So when it's 90 degree, you get a root 2F, the moral of the story. So whenever it's 60, whenever it's 120 degree, the resultant, if it's F and F, you get it as F. Whenever it's 60 degree and it's F and F, the resultant, you get it as root 3F. Whenever it's 90 degree, if this is F and F, the resultant, you get it as root 2F. So thus you get, so coming back here, whatever we were doing, so you get it as root 2F. So root 2F is the, root 2F, what am I writing? Root 2F becomes my resultant, and that has to be added with this F2, which is between Q1 and Q4, and you should know this distance. The charges are same, doesn't matter, but the distance is different. What will be the distance? It will be root of 0.2, the whole, so this is L square and this is L square. Say this A square, and supposing it's A and A square is a rectangle, it's a square, right? A square plus A square is the root of 2A square, which is root 2A. Therefore, you know this distance is root 2A. So based on that, the force will change. That force will have 1 by root 2A the whole square. So I'm sure you got the hint. You'll be able to do the sum. Okay. So that's it. I don't want to do more sums on this. This should be enough to last sums I've not done in detail, but I'm sure you understood. I want you to practice all these sums and be ready so that we can start doing the electric field concept. Till now whatever I was doing is only electric force. Next topic is electric field. So let me make a separate video for electric field.